uh, Hi Tony. So I skipped one of the example problems, that applications of the linear first order differential equation. I skipped one of those problems because that involves some electrical circuits or something. I don't want to involve in that. Okay, that may be easy, but I am not that much interested to read even that. Okay, so now we go to the section that we skipped, logistic equations. Okay, what does it say is nothing but population growth and bacteria growth, whatever you can say, the growth. So we continue that. The section 4.4, logistic equations. This involves the population growth and bacteria growth or radioactive decay. Population, or we can say that bacteria growth or radioactive decay, radioactive material. The radioactive material decays in the exponential rate. So we studied all these two topics earlier. So we are going to study and solve some of the problems in the differential equations perspective. So as we already know that we know that, for suppose if a population of a city, let's take that of a city, P of t is exponentially increasing, then its population P of any time t is in this form, standard form, P naught into e to the power of r into t. Okay, where this is the equation we used to solve the population growth problems, right? That means the rate of change of the population is directly proportional to the population. That is, this equation comes from the basis of the rate of growth of population is directly proportional to the population, right? For suppose initially there are large populations, then the growth of the population is also the very high. Now we can, the rate of growth we said here it can be the rate of change of the population. Okay, for suppose if there is a pandemic which is much more powerful than the coronavirus right now, then the population of a city what do you say, that it exponentially decreases because the spread is too much and the death cases will be too high, so that it reduces exponentially. Okay, not a linear fashion, obviously. For suppose if any epidemic is there, it spreads very rapidly. So you see the growth, not only growth but also decay, we can anticipate that. So this is nothing but, if we put it in the mathematical form, it becomes d, for suppose p is taken for the population, dp by dt is directly proportional to the population p. As I said in the previous day, if we remove this what do you say, if we had to remove this proportionality sign, we what do you say, we invent a proportionality constant. Let that be r. dp by dt is equals to r into p. This r is proportionality constant. Okay, so this r is called something else here. We will see that one later. And we see this one. When we differentiate this, when you differentiate this equation, what do you get? For suppose, what is dp by dt? So this is p naught into e to the power of rt. When you differentiate that, that becomes r into e to the power of rt. So let's say this is r into p naught into e to the power of rt. This entire thing is nothing but again p. So we have r into p. So either from through differentiation we can obtain the equation, this equation, or if we take what do you say, that if we integrate this equation, we will get the basic equation, this one, right? These are, we can go the vice versa, because previously we did not know the concept of the differential equation, so we use this equation. Let's say this is equation 1 and this is equation 2. Okay, now here the proportionality constant r is called something else, the rate of growth. What do you call it? Let me check that up. What is this called? The rate of growth. It is called rate of growth of the population. Okay, for suppose if any population, for suppose there is an earth, okay, what do? We have the America here, we have the earth here, okay. The population, human population on earth, for suppose now how much it is, like 7.5 billion. For suppose it can be raised, if it is rising, it can be raised to 15 billion. Okay, earth cannot able to sustain that population, and so many pandemics and much of the natural disaster phenomena happens. Even when the population is exploded this much, then naturally the population will gradually decrease to a point, let's say it is 10 billion, up to 10 billion. So this is called, see the earth can accommodate only 10 billion people, so that resources last we can use the resources like the natural resources we're talking about here, okay, without any fluctuation. So this is called carrying capacity of the earth. What we call carrying capacity of the earth for the human population. Okay, for any other animal population it can be high or low. We're talking about the humans. So this is called carrying capacity. What does it mean is there is a definition in your textbook, you can refer that, but I am saying it verbally now. The carrying capacity of an organism in given environment is defined as the maximum population of that organism that the environment can sustain indefinitely. Okay, this is the maximum population of the humans that earth can sustain. We can define like that. So this carrying capacity is denoted by K. Even any population here, even in the bacterial growth or any population, for suppose if there is a curd and you add some bacteria, see there is a milk, you add some bacteria so that it can turn into the curd. So if you put 1 liter of the milk, then there is certain number of bacteria only can present in 1 liter of milk. But suppose if you take 2 liters of milk, then double the amount of the bacteria can accommodate in that, right? That's how we go through the carrying capacity according to the nature of the substance which hosts the organism. We deduct that carrying capacity. For now, why it is important is after the carrying capacity, if it is after the fluctuation, see here, after the fluctuation it won't increase much, and it won't decrease much. Okay, after this it becomes 10.5 and 9.5, and it becomes 10.2 and so on. It fluctuates along that mean value. Okay, it won't decrease much and it won't decrease less. For suppose if we say this carrying capacity, if we involve in this equation 2, then it is reduced as dp by dt is equals to rp into 1 minus p by k. Okay, that means let's say this rp into k minus p by k. For suppose if our population p becomes the capital K, if p equals to k, then the k minus k, that is 0, that is rp into 0 is nothing but 0. That means dp by dt is equals to 0. That means there cannot be any rate of change in the population, or you can say that the rate of change in the population is negligible. Okay. This is called logistic equation. Now we solve. There is much about this equation is explained in the textbook. let's say, for suppose we solve a problem. Okay, we solve a problem in this. Okay, first let us solve this equation. We know the differential equations. First let us solve this equation, logistic equation. Okay, so dp by dt, we have dp by dt is equals to r into p into k minus p by k, where k is a constant here, r is also another constant, right? So we say that we use the method of separation, separable functions. By that we solve this equation, k by p into k minus p dp, that is equals to r into dt. Okay. See, we solve this. Okay. Okay, we go to the screenshots now. So we have that equation. Now we see that p into that is k divided by p into k minus p. If we see this, we can split this up in terms of, what do you call this method? B by k minus p, partial fractions, right? So this a and b are nothing but 1. You can easily find. If you take the LCM, then with this you can find, if you take the LCM, you find out what it can be, k minus p. Okay, you can check it out whether this can be equals to the k by p into k minus p or not, right? So we have now 1 by p plus 1 by k minus p into dp is equals to r into dt. Now we integrate on both sides to solve this one. So integration 1 by p dp plus integration 1 by k minus p dp is equals to integration r dt. So this one is nothing but ln mod p plus this is nothing but ln mod k minus p, and it is not positive, it is negative, because there is a minus p here, as we know. This one is equals to r into t, you can have a constant c. So when we solve this one, ln p minus ln k minus p is nothing but ln p by k minus p. You can have the mod here, there is no harm in that, rt plus c. Okay, so now p by k minus p is equals to e to the power of rt plus c is nothing but you can write c into e to the power of rt, where e power c is also another constant. You replace that with the c. Okay, right? So now we see here p is equals to k minus p c into e to the power of rt. Here k in kc e power rt minus pc e power rt. So we have p plus pc e power rt is equals to kc e power rt, right? So take the factor out, it becomes c e power rt kc e power rt. So p is equals to kc e power rt by 1 plus c e power rt, right? Now we solve this equation, right? For suppose if there is a given condition, for suppose if they gave any initial population that is when t is equals to 0, p is something else. Okay, they will give something, that means p of 0 they gave this something else. This p is in terms of function of t, so we can write p of t here, right? So in this way we can solve. Let us do one example here. The example of a deer, I think they gave one problem on the deer. Let's consider the population of white-tailed deer in the state of Kentucky. The Kentucky Department of Fish and Wildlife Resources sets the guideline for hunting and fishing in the state. Before the hunting season of 2004, it is estimated a population of 900,000 deer. Johnson notes a deer population that has plenty to eat and is not hunted by humans or other predators will double every 3 years. Oh, that could be some research paper, I think. This observation corresponds. That means, see this in the example, the deers in Kentucky. Someone said Johnson. Johnson said if the deers are not hunted by humans or other predators, they will be doubled for every 3 years, and the present population of the deer is 900,000. Okay, this observation corresponds to a rate of increase. R is given ln2 by 3, maybe we can find this 0.23. The data given in the problem, I'm just copying it, so that the approximate growth rate is growth rate of growth is 23.11%. Population densities for 32 counties in Kentucky, the average approximately 27 deer per square mile. Suppose that there is the density for the whole state, the carrying capacity. Let's say they say there are 32 counties in Kentucky, okay, and they estimated that there are 27 deer per square mile, okay. Then the average, the whole state of Kentucky is 39,732 square miles, okay. Then if we multiply these two, then we will have the maximum population that Kentucky can accommodate. The carrying capacity, we will find the carrying capacity of the Kentucky state of the deer population is 27 39,732 is nothing but this is 4 to the rate, let's say that 1,072,764 deers, okay. Now the questions they asked, this is the data they given. Now the questions they asked is okay. Okay, they asked us to form an initial value problem, okay. First question is, let's say, form an initial value problem. So previously we've seen that dp by dp by dt is rp into 1 minus p by k. We substitute these equations and p naught is given, okay. Then we form the initial value problem here. So what is that problem? So dp by dt is equals to r is given, that is 0.2311 into p 1 minus p by the carrying capacity 1,72,764 deers with a p naught, the initial condition p naught is 900,000 deers are there, okay. Next question is solve the initial value problem, okay. The second part of this question is solve it. It says to solve it, so we are going to find what is the p. Before we solve the general population growth, right? So that is p is equals to, what do we get? How to solve that? We got something there, right? Okay, let me check that. P of t is equals to c k e to the power of rt by 1 plus c e to the power of rt, where r is known, k is known here. So this becomes c. Okay, let's find out what is the we find out what is the p naught here. ck e to the power of r into 0 by 1 plus c into e to the power of r into 0 ck. E power 0 is nothing but 1, so 1 by c. K is a known figure here, so that is p naught is also known, that is 900,000. K is 1,72,764 by into c by 1 plus c. Now c by 1 plus c is equals to 900,000 by 1,72,764. That is some constant. Let's say some, what is it, constant? That could be, let me calculate that. Holy shit! Okay, for suppose if this is some constant capital A, okay, how do you find the c by 1 plus c is c by 1 plus c is, say this c by 1 plus c is capital A, so c is equals to a into 1 plus c is nothing but a plus ac. Now c minus ac is nothing but a, so take the factor out, c 1 minus a is equals to a, so c is nothing but a by 1 minus a, so this is equals to a is nothing but initial population p naught by carrying capacity k, 1 minus p naught by k. So what do we got is p naught divided by k is k minus p naught by k. Let's say these two cancel out each other, we end up with p naught by k minus p naught. So c is equals to p naught is 900,000 divided by 1,72,764 minus 901,000. So 900,000 divided by, this is 172,764, and if this is divided by, then we have 5.209. Let's say the c, we found out the c, so the differential equation is p of t is into k ck e to the power of rt divided by 1 plus c into e to the power of rt. C is 5.209, K is 1,072,764, e to the power of r is 0.2311 t by 1 plus 5.209 e to the power of 0.2311 t, right? So we need to product these two. What does that become? Okay, you divide both the numerator and numerator with the 5.029 so that you can cancel. So the numerator remains 1,072,764 e to the power of 0.2311 t divided by 1 by 5.209, that could be 0.19196 plus e to the power of 0.2311 t. Okay, this is the solution for the initial value problem, right? So he asked us to, let's see what is the next part of the question. According to this model, what will be the population in 3 years? Recall that doubling time predicted by Johnson for deer population was 3 years. How do these values compare? Okay, so in 3 years it will be double, right? Let's make a note of this one. Okay, we'll use this in the next problem. So p of t is given by 1,072,764 e to the power of 0.2311 t divided by 0.19196. Okay, so Johnson said that in 3 years it will be doubled, right? So we are going to find p of 3. So this is 1 million. What is the actual? This is actual population. He wants us to find out. Okay. Okay. For suppose, what is the population in 3 years? You find what is, if t is 3, find what is p of 3. 0.72769 e to the power of 0.2311 into 3 divided by 19196 plus e to the power of 0.2311 into 3. So when you calculate, this one comes as almost equal to 978,830. Okay, but by the Johnson's approximation, let's say, see this, in 3 years, this is the present population. In 3 years it must be doubled. Let's say it becomes 1.8 million, let's say. But our problematic approach, we found this is the population in 3 years, but this is by the Johnson's estimated that it can be double since this is greater than the carrying capacity K, that is 1,072,764, right? That's why 764. That's why this value cannot exist, and this value must be reduced. So let's say our population is at time, let's say this is time t, this time population at a time 0 is, let's say, 900k. Okay, so the curve of the population will be like this. Let's say this is the carrying capacity, that is 1.7 million, 1.072 million. Let's say this is the asymptote for the graph. So it rapidly increases slowly, and then slowly it grazes the function at the infinity. This population curve touches the asymptote, that is carrying capacity, at infinity. Okay, that's how the graph will be. Okay, next, see what is the next part of the question. So next part of the question, suppose the population managed to reach 101.2 million. Okay, population managed to reach this much. Deer are there. What does the logistic equation predict will happen to the population in this scenario? So what does it say is, that means our P of t in the current situation is 1.2 million deers are there, but the maximum carrying capacity is this one. What does happens now? Okay, we see that our equation dp by dt is rp into 1 minus, it is p by k, right? So if p, see this is rp, k minus p by k. So k is 1.072 million and p is already 1.2 million. K minus p gives you a negative value. So dp by dt is negative. That means the rate of change in p is negative. That means p is in decreasing mode, right? So we can be able to find initial population. So p is in decreasing mode, like let's say the curve of the p in this scenario, let's say this is 1.2 million, the carrying capacity k is 1.072 million. This is the k. What has happens in this scenario is, from this point the graph try to reach the carrying capacity and it touches that at infinity, but I made it touch earlier, sorry for that. This is the carrying capacity. So how do we can we be able to find the equation for that? Okay, to solve this, we try to do the approach. Let us say that it is the solution to this equation rp 1 minus p by k is nothing but p of t is ck e to the power of rt by 1 plus c e to the power of rt. We know r is 0.2311, k is 1,072,764, and he said our present population is 1.2 million, that is 1,200,000 deers at present. So we take this as an initial value. Okay, so we substitute p naught here. P naught becomes ck by e power r into 0, that is 1 plus c. So 1000, we did this earlier. So 1 plus c by 1 plus c is nothing but by k. Let's say this is p naught by k. So c is equals to 1 plus c into, we solved this one earlier, that means this type earlier, right? So it becomes p naught by k plus c into p naught by k, c minus c into p naught by k, nothing but p naught by k. We take the factor out, it becomes 1 minus p naught by k. So p naught by k divided by 1 minus p naught by k. So p naught by k, k minus p naught by k. So it becomes p naught is nothing but 1.2 million, k is nothing but 1,072,764, minus p naught is nothing but 1.2 million. So our c is negative, right? So this one almost comes as minus 9.431. Okay, so our equation, so if we substitute here, if we substitute this c, let's see, if we substitute this c in the equation given here, we get another equation p of t. Okay, that's the solution for the fourth one. So we analyze the case, what happens if the population which is exceeded than the carrying capacity, then it must reduced and it must come to the carrying capacity. The graph I given you there. Okay, this is the example. So with that it ends that problem, ends that section. So we seen that what is the logistic equations. deals with the population growth or decay, right? So we already solved that earlier, not without using the differential equations. Here in this case we are using the differential equations so that we can substantially analyze the results. Okay, here we learn two more terms in the section where p of t is okay, p of t is p naught e to the power of rt, where r is the rate of growth. Okay, if we solve that the dp by dt is rp into 1 minus p by k, this k is carrying capacity. That is the only difference I can find between our previous non-differential equation approach and to the differential equation approach. The involvement of these two makes problems very much interesting. So we stop here. We'll see what's next. I will catch up to you and later tomorrow.